50th Ananthakrishnan Colloquium. So today also a special day. We have reached the 50-year mark over the years, and as it sounds, and we have an eminent speaker today also with us. So I'll introduce our speaker today. He is Professor Bishakhdutta Gayen, and he is a specialist in geophysical fluid dynamic research. He worked to better understand the ocean's circulation and how it regulates heat and mass transport, including polar mass laws. His group developed, in fact, a fundamental physics of deep overturning circulation of oceans, which may be of interest to many of you, including the complex dynamics of melting of Antarctic ice sheets and etc. in a warming environment. And they use HPC quite extensively for their research. So introducing the speaker, he holds a bachelor's degree in mechanical engineering from Jadavpur University, Calcutta in 2006. And then he moved to JNCSR, where he did his MS and on a topic of rheology of frictional granular shear flow using MD simulations. And in 2007, he joined UCSD, University of California, as a PhD student at the Department of Mechanical and Aerospace Engineering. His PhD work was focused on turbulence and internal waves in tidal flow over topography via numerical experiments, including LES and DNS. And he was part of the GFT group at School of Earth Science in Australian National University from 2012 to 2018. Then he took up as a position of assistant professor in CAOS. Actually, he's holding a dual position, one at the Australia as an associate professor at Mechanical Engineering Department at University of Melbourne, and also he is holding a position as an assistant professor in CAOS at IASE. So he has published a lot of interesting papers. It looks like his favorite journal is Journal of Fluid Mechanics, Physics Review Letters, etc., GRL, JGR, etc., PNAs, etc. I have just glanced through his publication. It made me quite dizzy. Okay, so with this, I give a warm welcome to Professor Bishakhdutta Gayen to our Ananthakrishnan Colloquium. Over to you.
Thank you. Thanks a lot. Such a nice introduction. And I feel like hopefully I can give you some good talk based on this introduction he introduced me. Okay. So before wasting not much time, so let's dive into the topic. Okay. So today we'll talk about ocean circulation in a different perspective. Okay. And I'll try to, at the end of the talk, let's see how much I can convince you this perspective. And it is a kind of an alternative way of understanding ocean circulation apart from a ocean general circulation model. Okay, this is just a quick overview with the areas I was working on recently. One is the active area is the upper ocean dynamics, which is I'm not going to talk about this one. Then another big area where I'm largely connected with the Antarctic ice melting and Antarctic margin type of simulation. And then another big thing is the global ocean circulations. Actually, if you think about all are connected to some mechanism, okay, and that is like a kind of like a trigger me to look at in this different area. Okay, now. So today's talk is mainly focusing on the overturning circulation. I think this audience, I think this is redundant slides. Okay, you all know what is important. Okay, so I'm not much talking about here. One thing I like to emphasize here, the circulation is actually required to transport heat and mass. That's like a requirement for any circulation or vice versa. Okay, because heat and mass transfer is support the circulation support heat and mass transfer. This is like a kind of fundamental link. Okay, and then of course, through that one, it regulates many things, okay? And definitely it is influence the atmosphere and climate and weather in a long term and short term. Okay. Now, next is when you understand any system, like any circulation is nothing but something like you can think as in a physicist as a dynamical system. A dynamical system, we need to understand for sink and source. Okay, so what are the source? And what are the sink, because they are required. Otherwise, you will never get a quasi-steady equilibrium. We know ocean circulation is constantly changing. It is not in equilibrium, but there is a dynamical equilibrium there. Otherwise, the system will drift from its position. Okay, so that's why I categorize this energy source into two parts. One is called buoyancy forcing. Okay, and under the buoyancy forcing is called heat and salt, right? These are two give the changing the buoyancy. Buoyancy is another way you can think about the density. Okay, so high buoyancy means is low density. Okay, so this is like a density and buoyancy is highly connected. Okay, now another bigger force in the ocean is because we have the atmosphere and we have the gravitational force by moon significantly. That will gives us the two other mechanical forcing. One is the tidal forcing, another is called wind work. Okay, so this will comes under mechanical forcing. Okay, now as I told you, there is a sea of energy. Okay, so where this energy actually get drained from this large system. So mostly this forcing is happen over a large scale. Some forcing actually also happening in the small scale that will I'll talk about. But mostly this tidal force you actually churn the whole ocean water column, and you can think same as the wind. We also have a large scale or small scale. But overall, these are acted over a large scale. Now, all the energies are from the ocean by the small scale. Okay, here we just put it some important. There is more there. These are the most dominating one. See, bottom drag, bottom turbulence, interaction, small scale convection, near surface turbulence, okay, loss of balance, like you get this front pervasion, okay, barotrainic instability, all the way the energy is actually drained out from the system, and interaction with the ocean boundary. And this is the schematic of the ocean. There is an atmosphere at the top, and you can see the air sea playing a very important role of exchange of these energies. Of course, there is also another term called inverse cascade. This is not the topic of commercial discussion here, so let's keep it here. Okay, now next, community here, you already know that wind is actually playing a big player of forcing the ocean, and the pattern of the wind is very important. Okay, so let's move this slide quickly. Next is this is one is I like to spend more time in here. The distribution of SST, SSS, and SSD. Okay, SST sea surface temperature, SSS sea surface salinity, and SSD is the sea surface density. Okay, so the two biggest contributors for the density is salinity and temperature. Okay, now why you get it? That because of the sun solar angle and many other processes, correct? Like you have this evaporation, precipitation, and then ice forcing. So all this kind of a buoyancy forcing, of course, the wind is also playing a role to distribute the buoyancy forcing, like a drifting of the sea ice. But anyway, we categorize whatever is coming as a flux of salt and a solid fluxes and temperature fluxes, we call as a buoyancy forcing. So because of this buoyancy forcing, you get this distribution of temperature. So one thing you can notice here, SST is really high at the equator. As you go to the pole, it doesn't matter which ocean basin we choose. Okay, so the one thing you need to highlight here, this is Atlantic, this is Pacific, this is Indian Ocean. Indian Ocean doesn't have the north and south, but from these two oceans is a very symmetric north and south, except the Southern Ocean dynamics here. That is I'll talk about soon. Now, SSS, because of this precipitation and evaporation, it's such a nice SSS distribution. So SSS is not about symmetric. There is a lot of fresh water is actually sitting in the equator, and then just above the equator, mid latitude, there's a lot of SSS there. Okay, there's a lot of salinity there because of high evaporation. More and more you go to the pole, then the SSS drops, and that happened because of the melting. A lot of fresh water come from the polar ocean, Arctic Ocean, say for instance from the north, and then Southern Ocean, a lot of melting is happening. Okay. Interestingly, when you look at SSD, it is very much mapped with SST. So it looks like temperature has been playing a very important role of dictating density. Okay, so the density is really low in the equator. As you go up, the density increases. Okay, but it is the present scenario. Okay, it can be changed, right? Because if the salinity is going to play more role density, then this scenario might change. So we start getting the input of the salinity on the SSD, and that's like a kind of like a one of the important matter for today's discussion or today's talk. Okay, now next one. Just quick overview. This circulation is, if you look at any textbook, it is always present as a very complex nature. Why is it complex? Because they're connected Okay, now we are not talking about just a single basin. Say for one basin is say for Indian Ocean Basin, Pacific Basin, and Atlantic Basin, right? Circulation, they have their own circulation, and because of their own different dynamical coursing, the circulation pattern is different. At the same time, there's a Southern Ocean there which actually connect all the ocean basin. Okay, so it's something like this is like kind of like a big highway. What is all the highways come to the one city, and then you make a and then again they go back. Okay, so this is the way Southern Ocean play a role, and this is another very nice schematic from Lintelli's book. This is the way the water mass comes in the Southern Ocean and then redistributed. Okay, and definitely the Southern Ocean playing a very important role, because if there's no Southern Ocean, all the water come from the equator and just go there and melt the whole Antarctica. So this is Southern Ocean is playing a very important role, dictating the climate also. Okay, so this is like I'm choosing one of the ocean basin, and there's one of the favorite ocean basin I always like it is the Atlantic Ocean Basin, because it has the very symmetric, or it has a very nice two cell structure. Okay, this if I choose for Pacific Ocean, it is a very similar. That doesn't have much deep water formation in the north. About the deep water formation, what is I trying to mean in here? This is the your Antarctica side. This is your the Greenland, right? And this is I'm taking a cross section of south to north over Atlantic Ocean Basin. Okay, and you can expect, as I told you before, all the average. Okay, so density is dictated by temperature. So if you remember the distribution like SST, that means there is a buoyancy gain here, correct? If you actually making a buoyant fluid or less density fluid there, and then more go to the pole, there is a buoyancy loss there, because you are creating higher density fluid by buoyancy loss. Okay, creating more denser fluid. Okay, so that's the reason you actually get sinking. So we call as a convection. Correct? So this is a vertical convection. We'll go through more like what is we mean by convection here, and what is the other convection I'm going to start to introduce you. So here, just think of you creating a lot of dense water here, and this dense water is actually sink to the bottom of the ocean. Now there is a differential buoyancy loss there. Okay, that's why one dense water is always above another dense water, and that's why you get this two cell structure. But always Antarctic sector you get more buoyancy loss over. As you can imagine, the Antarctic section has a more buoyancy loss because there's more sea ice there. Okay, and during the sea ice formation, okay, that is another interesting. During the sea ice formation, what do you get? You will release the salt. Okay, when you release the salt, ocean get more salinification, it increases density. That's it. And then it think. And this is such a nice two-layer structures is we getting. Why we care about? We care about because this circulation takes all the heat which is ocean absorbed in the equator and redistribute it. Imagine this circulation is stopped. What will happen? All the heat is going to get in the upper ocean. It doesn't go to the deeper ocean and doesn't go to the pole. So pole getting colder and subtropics and mid is getting warmer. And you know that is another biggest problem in the because once this will happen, atmosphere immediately respond. Atmosphere circulation is going to immediately change. So that's why we need to pay attention who is actually controlling and what are the consequences in a climate change scenario. Okay. Now, this time talking about as a deep ocean. Now there is another thing is there when you just look at from the surface, there is a call is the gyre, right? And we always know that these gyres are always symmetric, symmetric between the equator. So always there's a subtropical gyre. Some of the ocean basin we have a subpolar gyre. Say for Atlantic Ocean, Pacific subpolar gyre is very small, and some have also subpolar gyre like Weddell gyre, that Ross gyre. Okay, so those many gyres are the subtropical gyre. Indian Ocean is very interesting. It doesn't have a lot, so it has a more prominent gyre in the south, correct? So this is you get the surface current, right? Now, next, what is the biggest surface current? Oh, yeah, this is the just showing the what do you call a satellite picture of the surface current. Now, this is the last one, the largest surface current. You can imagine if you remove some current to uninterruptedly rotating around the planet Earth. So that will be the strongest surface current, and that was the Southern Ocean, because it's uninterruptedly moving all around the Antarctica, and it's very dynamic in nature. It is full of baroclinic eddies, and a lot of instabilities are there. Now, saying that, why we are so much caring? Because we still don't understand who is actually playing a dominant role of this circulation. Why is that? Because last decades, so constantly people are saying, maybe you came, it's a very recent news also came that the Atlantic bottom water, everything is slowing down. Okay, and this has been reporting for last almost 15 years, like there is a signal of variability. Sometimes people thought about it is a variability, okay, but now the people are clearly see it is a declining signal, okay, that overturning circulation is declining, okay. Now, any index they choose and they will be founding. Now, next, there is also simultaneously people are actually measuring oxygen at the bottom of the ocean, okay, in the open atmosphere, and through that they try to understand that what is the convection is happening. As I mentioned about it, the largest or the highest dense water formation happening in the pole, right, either in the, towards the Antarctica or in the North Pole. And the people are seeing this, what is called, people are observing this study, the area of convection is also rapidly reducing, okay, either in the north or south, okay. So that makes such a like interesting. So overturning circulation is slowing down and convection is slowing down. Is it any connections? Okay. Now, there is also, there is a like long-standing theory, and that which is actually not supposed to move forward beyond that role of convection in ocean circulation. This comes from very, very famous group, probably many of people have heard these names. Okay, so they given this recipe of the overturning circulation, and they're saying how much is the energy, okay, goes to overturning circulation, maintaining the overturning circulation. And these are the, I just mentioned about before, right, the energy sources. So you can see every has some number. When it comes to heating and cooling and evaporation precipitation like salt flux, the number is written absolutely 0. That means heat salt fluxes doesn't do anything with the ocean. So that means they are not going to move the water themselves. Okay, so that is kind of a surprise me. So then, if you want to justify that, then you have to find the opposite route to drive the circulation or instant circulation. What is the opposite route? Okay, what is that? So there was a very, very famous experiment that was in 1916. Okay, and what is they saying is, interpreting ocean is not atmosphere, because you know in atmosphere we mainly cool at the top over the sense, right, and bottom of the atmosphere usually heat. So it is actually a heating and cooling or buoyancy loss and gain happen at the different geopotential level of atmosphere. Ocean is not, okay, because it's ocean, except some geothermal plume in the bottom of the ocean. As I come to here, ocean is mainly give the buoyancy fluxes at the top surface, okay. So now the sandstorm theory says, based on some very old experiments, saying like it is not possible to drive a full depth circulation. He mentioned about it cannot possible is a big overturning circulation just putting a buoyancy flux at same geopotential level. So this is like a kind of like people just use as a and then move forward. And then people say, okay, if it's buoyancy is not playing the role there, what is the alternative? Of course, it comes a mechanical forcing, and that is the reason it comes like a lot of theory has been developed around that, how the mechanical forcing is driving it. When it's a mechanical forcing, then back again, wind, we are thinking about might be wind is playing a very role to driving these overturning circulations. Next one, mixing. That means we call as a ocean stratification. Okay, think about, if I think about mixing as a dissipation. So I'm driving it up. Okay, car is driven by petrol. Right? And another thing is the road breaker, right? So if I tell you that road breaker is actually decide the speed of the car, it's not obvious, but definitely petrol is a very important player of driving it. Okay, so that is the logic is come. Is the frictional force is important? okay, driving oceanic circulation, or still that source of energy is playing important role. So this is like we have to again this between the sink is important or source is important. And even we think about source for buoyancy force not important, that means back to again wind mixing is very important, correct? Or wind and tide is important. So that's why last 30 years we are always talking about okay, wind or tide or mixing is important or wind is important. So that is where most of the theory has been developed. Of course, in the back of the envelope, there's also another thing is coming. I'll just come to that. So after this, all the scenario, you see there's a big knowledge gap there. Okay, so that means we still don't understand the exact role of the buoyancy forcing in the overturning circulation. And then another things, we also don't understand how the convection is connected with the large scale overturning circulation. And why you don't understand? Because these two things is actually small scale. And we have a limitation of resolving this one. So that means it's again goes down to how you better representing these two system in your model. So they are very much depends on the parameterization. Okay, so this is the three big question around ocean circulation, and we still need to answer this question. Now, why is the difficulties? Of course, everybody has a limitation, as I told you. When you talk about the GCM, okay, global circulation model, the biggest models we have it like a either MOMS, many people are using it, okay, and in GCM you probably know MIT GCM, they have a real limitation. If you want to resolve the scale, say the basin scale, it cannot be possible to resolve the smaller scale of turbulence. That is obvious because the scale separation is huge, okay, from one scale to another scale, correct? Then to a DNS community, they are also struggling because they cannot scale up because they have to resolve the small scale of system. Small scale means after the scale, the energies disappear. Okay, we call it either for a momentum we call it thermal scales, or for salinity or temperature we call it a bachelor scale. So they are very small for ocean. It's less than millimeter. So that means there's a big scale separation, and then of course LES is also playing a role. Try to bridge the gap. Then more this era, we start to rely on the reservoir scale modeling, correct? And that is the way we can bridge the gap. But really, there is a big gap there. Okay, and where we have to, this is like a kind of a very high resolution model. This is not a climate model, not running for 100 years. So we can afford to run this model because this is a high resolution model. It's run by my colleague at ANU. And this is 1/10 of degree model. They are called access OM2. Many people may be familiar with that. So that output is also exists. So that model, they are only resolving above, they just about to resolve the AD. We call it the AD resolving. All the is resolving because if you think about AD, it is nothing but motion, right? It's swirling motion. There's independent swirling motion in the turbulence level. It's also the AD, right? Do you think we're resolving? No. We're resolving what kind of a mesoscale. Or still we are not resolving the submeso. If you have saw the diagram, the submeso scale where you start to see the sinking mechanism. Okay, the energy start to sink, not in the mesoscale, because in the mesoscale you get the strong geostrophic balance. Okay? So now this is the your limitation, and then you know also, right? Observation is always very difficult. It is a difficult in terms of time and the space. Okay, so always there is a complementary research need to be done. Okay, so this is another complementary approach we what is called we initiated. What is that? We rely on the dynamical regime. Okay, this is the concept of, because being as an engineer, I get very fascinated by this one. We people actually working on the rotating table. Correct. This is the first time when I see rotating table back in ANU when I started my postdoc. They're saying like we can rotate the whole planet Earth in this 1 meter domain, and then ask them how we rotate much faster than the planet Earth. That's it, and that's why we get the big scale inside the domain. We only care about the Rossby number, and the way we increase the Rossby number, rotating faster. Okay, so this is a very good idea. So this is very similar to we give the condition which is matters a lot. Okay, the same concept, you know, right? When the ISRO they make the the spacecraft, they usually test it in the wind tunnel, and they test it very small setup. Okay, so let's do this. Let's use this concept for oceanography. Okay, so we rely on the dynamical regime, and then we can run this DNS, LES, and lab three together, and try to establish this model, and then we produce the data. Independently, we use the theoretical approach, get the scaling law, and validate the scaling law, and then plug this. That I come to this formula. See, for like scaling law means forcing equals to circulation, and in between is the coefficient. Okay, it sounds very simple, but it is the main conclusion. You have a forcing, and then you get the product. Okay, and the coefficient will be evaluated based on the data, correct? And the data where you can trust, which is comes from the observation, it comes from the DNS, LES, and lab, where you know we are resolving the small scale, correct? And then we can predict it back observation. Can we predict it? And after that, we get a kind of a predictable model. And based on the scaling is also very helpful because we can translate the scaling to the large scale ocean model. They can use the scaling, okay? Because for them it's very difficult. So where it is possible, they can use the scaling. That's like kind of mindset. But of course, we are losing something. There's nothing is perfect because it sounds like it's a very simple job, but still in the deciding this regime is extremely difficult because it has so many parameters, particularly ocean, right? We are here not talking about dimension of the ocean anymore because the dimension is kind of irrelevant. We come up with something non-dimensional parameter. You probably heard about Rossby number, right? That is everybody knows. So similarly, in community or fluid mechanics community, we are very interested about the Reynolds number, right? Another number, Rayleigh number, right? More and more, of course, Rossby number is similar to Ekman number. We talk about Ekman number. There's a Atwood number. So you have so many numbers there. Not every number important. This is my whole parameter space. And why is still difficult? Okay, we can't go with this number. We need to achieve this number. This is we're going to achieve it. That means we're running this alias DNS in the ocean because ocean is constrained by these numbers. And look at this number. The Rayleigh number, which I'm going to define it, is very large. Is a very large for the ocean, and we're not able to. We can't claim that with the lab and with the DNS alias we're going to achieve this number. Okay, Reynolds number is also large. Rossby number, some number is there. I'll talk about this one. We can achieve this number. Aspect ratio. Never ever we can achieve this aspect ratio for the ocean. It's a thin sheet of paper of the ocean is. Okay, so the dimension of the depth is much smaller compared to the horizontal extent. Not like atmosphere. Atmosphere aspects are much larger. So that is posing a big challenge doing this experiment in lab or in a DNS or LES setup. Okay, now we can dive into the problem. When people talk about convection, what is usually come in the mind? Okay, the most ideal case of convection is the Rayleigh-Bénard convection. Heating from the bottom, cooling from the top. That's like the first thing we come. And we define by this non-dimensional number called Rayleigh number. Rayleigh number, nothing is the strength of the buoyancy compared to the viscous. So very large number, we actually get a very rigorous turbulent flow. Okay, up and down motion. What is the purpose of this flow is? Transferring the heat from the bottom to up, vice versa. Okay, that's the whole purpose. Now, if you pay attention, if you look at a zonally average, do you get any mass transfer? No. We never get a mass transport, but we get a heat transport. So that's like a very important conclusion about a idealized convection. You always get up and down motion. If I look at a horizontal average sense, whatever going out, going down, so will be zero, cancel, no mass transport, correct? And we define this heat flux. So there is a heat flux is going from the boundary. So heat has to grow from the bottom of the plate to the top. Now, ocean is not like that. Ocean is like this. There is a not necessary heat should go from the bottom of the ocean to the top of the ocean. It not necessarily you need a motion go all the way to the bottom of the ocean, not like atmosphere. The atmosphere overturning circulation is very easy to understand because of the atmosphere is cooling, bottom of the atmosphere heating. So there is a tendency you can drive it, but this one is not easy. And also at any depth, if I integrate, the heat flux is zero. The vertical heat flux is zero. And here we also define a number the interesting way where we are not interested about the vertical. Not interested in the vertical scale, we interested about the horizontal scale because that is the where we giving heat flux. So this Rayleigh number definition is little bit different than traditional Rayleigh number definition. Okay, here we have to rely on available potential energy. I'm not going to bore with the derivation of available potential energy. So the simple concept, potential energy is not the only one. Okay, how much is the potential is the available to you? Say, I'm standing like this, I'm standing upside down. Okay, when I have a chance to have a fall? When I'm standing upside down. Both may have the same potential energy, but one is available to you. Okay, so similarly, you can see here, the both when creating an artificial system, you see the one streak the other side, and I'm creating the another streak other side, and this both the streak which is decided, which is situated at the top surface, one is the delta difference between one is plus delta rho, another is minus delta rho. Okay, so if you calculate the potential energy of the whole system, for this one and for this one is same. One case no density changes, another is you move one density delta rho one side and redistribute, right? So if you look at here and we put the so what will happen? There's a lot of dense over here, right? Which is actually try to go down. Okay, this is the one of the example of both system has the same potential energy. The system at the bottom has a more available potential energy. How you define it? For that, you might need to read this paper. Okay, I'm not going to do it. It's a very interesting way. Resorting mechanism. Okay, we have to resort it. And that is the way you get available potential energy. Simple way. When I teach in the class, I give this example. Both are the same potential energy, but this has a more available potential energy will fall. Right? And that is exactly why I say one has a more tendency to do work. Okay, and there you can extract work because in a dynamical system, potential energy gets converted from potential energy to kinetic energy, and through that system will be able to do work. Now, back to maybe it looks very funny how we actually understand ocean circulation. This simple fashion, and then slowly we add complexity. This is not you used to see this one. You probably used to see much more bigger system, more complex. But here, approach is opposite. We started with absolutely simple. Okay, we started with an idealized box like this. Even it doesn't have the other half of the ocean, right? It is just like from equator to pole. Either you can think about one side of the planet, or you can think of the other side of the planet. Okay, one is how we are doing it. Okay, and at the top surface, here we are cooling it, and another surface we are heating it. Simple. You can pretend that cooling is the buoyancy loss. Think as a pole, and heating portion buoyancy gain. What do you expect? It's not obvious that you expect a overturning circulations, right? Because according to the Sandstrom theory, back in 1960, he did this experiment there. He found this overturning circulation is not going to establish if a buoyancy source are applied at the same geopotential. Okay, this was done direct numerical simulation. In between, Rossby attempted, you know Rossby, right? Rossby attempted this simulation, but not in turbulence regime. He attempted much more smaller domain. And he able to see this overturning circulation, and he also see the feature of circulation. But people disregarded this. They're saying that, okay, this simulation is not even having a turbulence. So why we state ocean has to be a turbulent convection? Okay. So after that, we set up this model and we run the numerical simulations. As you're showing it here, you're showing a temperature field. You can think about density field. So you can see here, light density water is moving across the globe, right? And come to the pole. And here they is sinking. So this is not the sinking you see, or not the big particle motion you have seen in the Rayleigh art. Why is that? Because you bringing this warm, what you call buoyant water, right? Which is actually creating a stably stratification under the whole cooling patch. Okay, so that makes a stable boundary layer under a convective system. So top is you are trying to impose buoyancy loss, at the bottom there is a lot of what is called warm fluid is coming or lighter fluid is coming. So they're creating a stable boundary. So convection is not able to penetrate even if you're cooling the half. So they wait at the end wall and finally able to penetrate this boundary and then going down and then is coming back. Okay, of course it doesn't look like ocean, but it is the kind of like first to understand what is the convection or what is the buoyancy can play a role of driving some kind of system which is we never regarded before. Okay, and another thing I like to emphasize here, you see this small scale, they are very, very dynamic. It is not even laminar, it is real turbulent convection. And of course, the non-dimensional parameter always and go through. One is the Rayleigh number here, another is a Prandtl number, because depending what is the scalar it is driving, like a diffusive between two scalar, and that is also playing a very important role. Will come when you are talking about two scalar convection system. Another is aspect ratio, as I told you, aspect ratio is a big challenge. Now, next, because of LPS, and we can learn from the DS, we can go much more bigger scale, bigger than the lab scale. Of course, it's real ocean. I told you, Rayleigh number is 10 to the power 25, 25. It's very difficult to achieve. Can we achieve at least somewhere? Looks to like you are achieving a dynamical regime. This is called dynamical, like we are achieving something so that we are getting some glimpse of the real system. Okay, this is the glimpse of the real system. This is done with the experiment. So we have very fortunate working with experimentalists back in ANU. So they did the experimental setup. So this is like the experiment in 1916 is we are reproducing this not only with what is called performing the same experiment, we actually able to go beyond, because in 2000th century we can have much more bigger, we can have much more control because there's a lot of heat loss associated with the experiment. And we actually proved that Sandstrom theorem is not wrong, is wrong, or is something is there's a flaws. Okay, that give you very encouragement to do this study. So that is kind of my first work at the when I started this work. It's working is a very controversial problem. Okay, but once we get this experiment, that the same kind of experiment is happening, daily is happening, I get very encouragement. Okay, and then I move, I take this thing in a much more complex, adding more complexity in the system. Another thing is I would like to notify here that you see that up and down. But now if you look at that, it is not only transferring heat, it transferring the mass. So this mass is coming from the equator, going by convection, and then upwelling is happening. So there is a conveyor belt is setting up. Okay, so that's the thing is like getting a linkage between this convection and overturning circulation, very simplified fashion. Okay, so the common knowledge around the textbook that convection doesn't do mass transport, that was is not fair. This is kind of very special type of convection. We call this name is a horizontal convection. Don't blame me, it is not given by me. Okay, given by this is one another very good theoretician. He gave this name in his textbook. It's called horizontal convection. Okay, and since then we call that convection as a convection. Some people very frequently call it the vertical convection, and this is called horizontal convection. So this convective setup, it is not a setting of small scale immediately. As I told you, forcing can set up small scale. This is another example there. Forcing can set up the large scale. So you can say you give a large gradient, okay, by heating and cooling at the two extreme of the pool and driving this overturning cell. In this process, you are upwelling the water. Okay. I promise you, we should come up with much more rigorous scaling. Correct. So let's think about the equations. Of course, in hand we have two equations. Equation. One is conservation of mass, another is momentum, another is advection diffusion equation. Correct. So let's see what is the balance. Think about very low number. Of course, low number viscous force are not important. If the viscous force are important, sorry. So that means at the low number, the balance is buoyancy and viscous force. Buoyancy and viscous term, right? Buoyancy is very important because it is negative forcing. So, and then heat equation, if you think of steady state condition, it is advection diffusion balance, right? So, two equation, two unknown. What is unknown we are talking about here? Let me see. Unknown is the circulation, the velocity. What is the unknown is there? Boundary layer. Because these very interesting things, we start to forming a boundary layer. Okay, boundary means something is changing with the depth. That is the definition of boundary layer is. So what is changing here? If you think about cooling, I don't feel like how is because it's a very complex structure. But when you actually observe heating, you actually creating a stable boundary layer because you're creating a diffusive boundary layer. So here we try to estimate this diffusive boundary layer, and that all these balances happen through this diffusive boundary layer. Okay, this is playing a very important role. Of course, that means we're actually building a stratification. Okay, that is over the stable, like where we're heating it. And once you know these two, you can get the scaling. Okay, don't need to remember, just to say that boundary layer, as everyone knows, when you forcing is higher, boundary layer is getting thinner. Okay, density is getting higher when forcing is higher. So we are very good. And this Nusselt number is nothing but it's a non-dimensional heat flux. That's it. Okay, because we are on the DNS one, we usually interested to talk about Nusselt number rather than the heat flux. Okay, because when you talk about heat flux, it doesn't make any sense because the heat flux is nothing to compare with the real ocean. Okay.
So in the momentum, you don't have rotation there.
I'll come. Next slide. Okay. Now, next theory. When you go to the number, viscous force is not important. There is a difference between inertia and buoyancy. Advection diffusion balance is still important. Right? Two equation, two unknown. You get the scaling. In the scaling, you get Rayleigh number and Rayleigh number product. Okay, just to say, like when you Rayleigh number and Rayleigh number product, it looks like there's a viscosity sitting there. The viscosity in the coming from what do you call it? In the definition is the new is there, but more in the viscosity, but the product there is no viscosity. So that means still is the diffusivity is important, but not the viscosity is important. That's like I'm telling. That is actually this equation telling you. We can test it. We tested these two scaling, both giving the same formula, except there is a shift. So that shift is when the flow becomes laminar to turbulent. Okay. So we see this interesting regime transition. We define inertial dominated regime and viscous dominated regime. Okay. But again, it's too much ideal case. Now is the thing is the rotation. Okay, now we understand. Okay, we understand the rotation circulation. When the rotation is there, what will happen? The balance is very difficult. Now is balance is come from the rotation term, right? So that means is you have the so covalent and buoyancy balance. What is the meaning of buoyancy balance? Nothing but geostrophic balance or thermal wind balance. So now heating and cooling, just think of the atmosphere. You get zonal jets, right? Heating and cooling, and it will not go from heating end to cooling end. It will go to the perpendicular. So you get zonal flow. That is exactly happened. Heating and cooling, non-rotational. This is the overturning circulation. This is the stratification is showing it, and overturning stream function is showing full depth. That once you change it, rotation, you get overturning is getting weaker. You get a lot of backlinking areas. Just like your atmosphere scenario, and you get zonal jets. Now, and will be constrained by geostrophic flow. Okay, so this is we in our term is rotating horizontal convection. We add the term rotation. Correct. We come to this re-entrainment channel. The channel we're talking here, which is doesn't have a obstruction in the zonal direction, just like atmosphere. It just moves like this. Okay, ocean. Some you can think about We'll come back to point. How many things like this type of configuration there in the ocean? Anyone? Any guess this type of configuration? Southern Ocean. Yes, I'll come to that one. Okay. Our target is actually understanding the closed basin. Let's come back to the closed basin and come back to Southern Ocean again. This is the closed basin. This is a geostrophic flows, correct? No, flow cannot link on the both side because both sides you have now continent. Think about North Atlantic, you have a continent. What happened? The flow has a tendency to go next to what is called equator. But the same thing the geostrophic established. What will happen? The flow will actually choose as a boundary currents. Okay, so it has give you a strong boundary current. Okay, I will come to this point. What is a boundary current? Then you get a zonal flow. Then it will get another boundary current, and then it finally sink. But hold on, this is actually creating some. What is that? Yes, this will actually change the stable boundary layer motion or the position, because previously stable boundary layer moves the width. Now the stable boundary layer is formed like a boundary current. It's hugging against each wall, except at the mid latitude. Correct? So now when it is flowed over the particular convective area, the convection is don't get the shielding mechanism from the bottom. Because you get this all western boundary current, eastern boundary current zonal flow. So what will happen? This convection will be as an open ocean convection. It directly sink even in the whole cooling patch. So no more like an wall. That is, you have seen it before. This convection is now as a two-way convection is happened. One is that boundary current itself is sinking, humming against one of the, and then there is also relevant type of scenario convection is happening over the cooling patch. So you see that two types of convection, and you know that relevant convection doesn't do mass transport. That is exactly does the convection hold the. You see, this is I'm increasing the rotation. This is my non-rotating scenario, and this is the rotation scenario. This is I'm showing the vertical isosurface, vertical motion. You see, there's a lot of vertical motion up and down, just like an angular. So this doesn't do mass transport. So what mass transport is done by? There is a boundary here. So that will take care of mass transport. Okay, so an associated in-global convection, or we can call as a side-global convection. Here you give the name. Okay, now we tested again the experiment. We happy. This is looking at the different view with the increasing rotation. Okay, so decreasing Rossby number means we are going to the geostrophic regime. So Rossby number matters. Okay, we have to achieve some number. We see the glimpse of turbulent convection, but Rossby number is a key player here. If we can match the Rossby number, we are able to see that we are able to enter the dynamical regime where the ocean is, and we slowly enter this dynamical regime. You increase rotation, even you vanishes the large scale. You get convection regime. Okay, we are not interested. We are interested between geostrophic flow and inertia regime. Okay, so this is the way we feel like ocean is lying, and I believe in the regime understanding. Now, let's look at the balance equation, right? As you mentioned, in the balance equation, now is the rotation term is very important. So we have to discuss the inertia term, viscous term, rotation and buoyancy, and still advection diffusion equation. We have no choice. Advection balances diffusion. Correct? So it makes you call geostrophic balance, and you get a geostrophic scaling, which is goes with the Rayleigh number, Aikman number. Sometimes you can write in terms of a Rossby number, like this is Rossby number. So just pay attention here. Again, it decreases with the heat class. That's good. Boundary is getting thicker with increasing the rotation. That is also acceptable, because more rotation will happen. You're getting thicker boundary layer. Okay. So we are very much consistent with this one, and we tested against both the experiment and numerical simulations. We get happy. Of course, That is, we are missing it here. Yeah, this is what I'm trying to show you. When there is a rotation, we're not talking about rotation, we're talking about only this axis. This is called resonant axis. This is my rotation axis. Rotation is increases this way, and then increases this way. So ocean is lying in the geostrophic regime, but sometimes the geostrophic breaks down. So it gets to the inertial regime. So it is oscillated between inertia and geostrophic regime. And we need to perform experiments that we can cover both the inertial regime and the geostrophic regime. We will say, even with LES, we still need to go further, right? That's the reason I put it, the ocean is another different scale. But we start to see the glimpse of ocean. This is like a next level of complexity. So far, I'm talking about rotation, that is a constant rotation. Okay, now I'm adding a variable rotation. Rotation is 0 at the equator, rotation is higher at the pole. That means I'm adding a beta plane. Everybody knows when you're adding a beta plane, you get Rossby waves, correct? And you also get gyre, which is scale of the length of the box. So we start to see very, very similar structure of the North Atlantic. This is the North Atlantic circulation where you're heating this side, cooling this side. This is western boundary current. The gets separated. Boundary current gets separated, blow as a North Atlantic current, and then goes in hugging the eastern boundary, blow as a North-Atlantic current, and then some countries go as a over the region. Of course, we don't have a topography, but this current is actually scenic. At the same time, you have a convection happening, and we start to see that the real system, this doesn't have any wind forcing. This is the first time, and a realistic, more like realistic setup, we able to show that buoyancy forcing, how buoyancy forcing is actually creating a gyre. Okay? This complex three-dimensional overturning. So overturning is whatever we thought about. We always think about overturning is only one plane, and gyre is only one plane. It's not true. They are connected. Of course, wind is playing a role there, but buoyancy can drive this gyre. Okay, and you see that this is the three-dimensional view of the overturning circulation. This is I'm chosen for a simple basin, one North Atlantic basin. Okay, now you see the two gyres and the circulation. Now, southern ocean, as I told you before, now you remove the continent. You drive this zonal flow, and this looks like Southern Ocean. Okay, so we here these simulations are adding more and more complexity. We adding wind force there, we adding topography there. But in the first step, we start to seeing whatever people start to observe it in an eddy resolving simulation. Blow more wind. What is wind? Because of wind pumping, it's stiffening isotherms, and then you creating the backlinik eddies. Backlinik eddies is transporting the heat in opposite direction, flattening the isotherms and decreasing the geostrophic difference, and you get a eddy saturation, right? So transport is insensitive to the wind forcing. As the thing is, we also found it. So we found it that transport is more sensitive to the buoyancy forcing. Okay. Now, just to summarize this whole thing, real-time channel buoyancy forcing drives the zonal current, closed domain. It is three-dimensional nature, and now back to the complex. You have this close, and re-entrainment. You get this 1, 2, 3, and then all three are connected, and the overturning is happening. Okay, and we also tested, and this is recently published in the annual review of fluid mechanics. We actually give very, very simple scaling. This scaling is, we are not proposing, this scaling is already there in the atmospheric community. We're just putting in terms of ocean context here and plugging the number where actually this matters for the ocean. This is the, I told you that this is the geostrophic scaling. This is written in terms of more dimensional fashion because that is the way oceanographer is very comfortable, because we can't present in terms of Rayleigh number, Ekman number. We present it in terms of dimensional fashion. Okay, and we plug the number. The white accurately predict the overturning transport and heat transport. Okay, of course there is a lot of, there's a lot of things are dependent here. One of the things is very dependent is the as I told you before. Okay, means the mixing. But this will tell you where is the mixing matters. It's like another question I'm actually asking myself, because we are talking about this balance, right? Where the balance we are establishing, that is the where is the mixing matters. So where is the balance is there? We're talking about the thermal boundary layer. So here, is it interior mixing is matter? At least, but not my in simulation that interior mixing of the ocean matters. It matters the upper layer of the ocean. Where is this mixing matters? Now, again, who is driving this mixing? That is the another seminar. Okay, so that was okay. Who is actually changing this kappa? But this is the recipe is actually tell you there is a things are very playing a very important role. And why is very important role? You can see here this alpha delta T, which is nothing but buoyancy forcing, right? Now here I'm only interested about the alpha delta T. In reality, in climate change scenario, what is the another one is creating the buoyancy? Beta delta S, right? So now that is going to play a role in the climate change scenario. More than this buoyancy forcing, and you know that freshwater is and equator is opposite, right? And more you are melting it, okay, in the polar regime. So that is a contradicting or reducing the buoyancy forcing. Okay, I can even understand this simple theory can not only explain the water circulation, it also explain the consequence in future. I convinced one of my colleagues in Norway run the GCM in a big system and check the number and what is called number killing. Initially, it didn't convince. We need to test it because otherwise, this theory will be just sitting in our paper. It's not going to translate it to the bigger community because bigger community means it has to be tested again the ocean model. We tested, we did so unphysical simulation with ocean model because if I say ocean rotation, you say why I'm changing the rotation. So I have to change the rotation to see that we are getting this scaling. So we see that this scaling is right or wrong, and we change this. We look at the southern ocean transport, and we see that southern ocean transport is function of alpha 1 by theta. This is geostrophic scaling. So southern ocean is very sensitive to the buoyancy forcing and 1/3 power. Okay. We change the southern ocean, it doesn't sensitive. Okay, so mixing is not changing the southern ocean, but mixing is actually changing the upper sail, not just changing the mixel. So it's when you do the structure is very interesting, and we're still learning why one sail is so much sensitive with the mixing, another sail, southern ocean, is insensitive with the mixing. But apart from that, both the sail and southern ocean is sensitive against the buoyancy forcing. So that's like kind of a good encouraging message. Now, based on that, we have to draw this diagram. How much is the time in terms of over?
It's okay.
Okay. I put very quickly. I'll go. Okay. So this is the way we actually revisit this, the textbook and try to connect the gyres and water turning. Okay. So this is the view of how the gyres and connected by the water turning. I'm not saying that gyres are not driven by the wind, but the wind is the not only one driving the gyre, or cannot be explained by the spare drop balance. Okay, because if that is true, because even if I didn't show the slide, there's a very recent observation they found gyre is also weakening. Okay, so that is give you a signal that gyre is weakening because wind field is not weakening. So then why is gyre is weakening? So maybe this is the buoyancy of the gyre which is altering. Southern ocean also, they are very much connected, and this is the picture. It's good for me, I have to draw it. Okay, now next one. I go faster. So I told you I'm going to add complexity more, right? So this next level of complexity, try to replicate the salinity. So we try to force the salinity now and temperature, and try to remove the wind for a moment. Okay. So we force the salinity, that means E minus force SST and SSS. We force the system. This is the what is called the red is the SSH and temperature is the blue color. Okay, don't look at what is called that 40 degree, 20 degree, because that's not important for DLS. If DLS is all about that dimensional number, this is the way we're going to achieve it. We have to put some number there. Okay, so don't get scared with these numbers. Okay, and then we show a very interesting feature. Okay, this is the salinity contour and this is the temperature contour. we see that, you remember the first figure, right? We always have a stable layer at the heating end. It's not just turbulence. What is the turbulence is there? Always the unstable part, right? In the real ocean, you see the bulging, right? Bulging of thermocline, the mid-latitude bulging of thermocline. This is not even wind forcing. We see the bulging of thermocline just for salt and temperature forcing. Because we now start to creating mixed layer by mechanism of salt fingering. Because we creating evaporation is there at the mid-latitude, right? So with the evaporation, we create convection. So there is a two convection there. One is the temperature, and this is the mid-latitude, the salinity. Okay, and this type of convection we call double diffusion convection. One is the diffusion convection in the pole and salt fingering pole. Of course, now is the big challenge for the ocean to actually resolve this salinity scale, because now the diffusivity between the salt and temperature is driving this convection. Who is diffusing first? That will dictate the convection. Okay, so that means we have to sort of take a focus how are we going to have a convection in a LES setup. Okay, so we have to still doing this method. And this is their salt force system, no salt force system. Can you see here? This is the temperature. You see, there is no bulging of thermocline in the mid-latitude. And the bulging of thermocline in mid-latitude, you can see the small scale structure here in mid-latitude. And here, no structure, only convection in the pole. Now, interesting. We can, DLS, you can do whatever you want to do it, right? We can run the system with only fresh water forcing. Fresh water at the pole and salty water at the mid-latitude. You get haline circulation, which is opposite to the thermohaline circulation, right? And this is the thermal case, which is only forcing by thermal, and it is the reduced magnitude, correct? This is only temperature, this is only salinity, add it, reduced magnitude. That means if I increase the salinity, what will happen? It will going to erode the thermal circulation. And the circulation is slowly collapsing. Okay, so this is a very new result. We're still understanding it. I just not talking about this one. This is the wind, because I always talk about against wind. Okay, and wind is also playing a role for circulation. We tested the scaling. We're revisiting the scaling. We're proposing some scaling based on wind, salinity, and temperature forcing. Okay, and very good. And good complexity, because we like the real system. This can handle the Antarctic margin. So this is the first DNA showing the Antarctic circumferential current. This is resolving all scalar motion, and it has a topography. And you actually see that where you require the convection is actually coming. This is two convections. Okay, and that's it. That's my last slide. And this is like a looking at the non-dimensional fashion. We compare oranges. I have to make it in orange and then compare it. So non-dimensional look at. So the numbers are not far apart, because wind is also there. So many other things are there, but we are working it. Okay, and that's the way I stop it here. This is like key conclusion. Want you to read, and then I stop it here. Thank you.
Can I have the mic? It's thank you, Gayen. It's a very exciting talk with theory and experiment. Any question before we jump into discussion? There's also tea arranged, so people would like to leave also have a tea before we leave. So now I invite discussions. Anybody has any question? Then we can take up. Yes, Bhupin. Oh yeah.
When we say the heat and moisture,
I'll give the mic so everyone can hear.
Dr. Vikas, a very interesting talk. Can we say that the heat and moisture regimes in the atmosphere can be analogically termed as a double diffusion?
Absolutely, because if you ask me ocean, I feel like ocean is atmosphere. I don't get this thing. They're very similar. Yeah, and moisture is really difficult to resolve it, and salinity is the same as very difficult to resolve it.
Thank you.
They're very similar.
Yeah. Next, Bhupin raised his hands.
Yeah, so the thing is, you mentioned at the end of your talk, like the gyre circulation, since it is mostly in classical literature, it is like wind-driven circulation primarily. So you told that winds are not changing much, but few of the papers have, I mean, not few, maybe many of the papers have told that in a warming environment, at least the tropical circulation is weakening. So in that case, let us say that the gyre circulation is also weakening. So have you checked whether the gyre circulation weakening due to winds getting weakened, and along with that, what is the salinity change? I mean, salinity and temperature, and has the density changed? Which one is actually driving more in the warming climate? Have you?
Yeah, so that was I told you I didn't get a chance to talk about. So we actually in the process of developing a unified theory of gyre in terms of all the forcing, and which is actually have, like, of course it's very difficult to have a linear combination. But if it's a linear, it's very good because wind is directly impacting the sphere drop flow, and sphere drop you get the what is called vorticity, and then also the wind is also playing a role of circulation, and over circulation is buoyancy also there. So there is a wind is actually coming to both altering the buoyancy forcing and directly actually giving the vorticity in the top surface. So that was like the next goal actually, and we were also like looking at it. This is a very good question actually. Who is there? Now of course again, this is very interesting. Like when you say the wind and see, there is always a debate. Technically speaking, wind is nothing but geostrophic circulation in atmosphere. Okay, and wind is also redistributing buoyancy. You cannot remove buoyancy without wind. If it's done in the atmosphere, the buoyancy distribution is going to get changed. So I think we need to understand is more fundamental the processes, right? This is the wind and buoyancy.
I think adding to that, what wind does is it holds the buoyancy forcing in place.
Yes.
That's the role of wind actually. And that buoyancy force itself drives the wind. We call it coupled system.
Yep.
So yeah. Good. Next, Anubhav. Yeah.
Yeah, Dr. Gayen, very nice talk, particularly the fundamental process you are talking about that. But what is the take-home message? Means you are talking about that how DNS is important for this thing, and a couple of slides you have shown GCM applications. So how you think that the DNS can help that whatever the biases in the model, basically the couple model, how we can resolve it? Number one. Number two, that for DNS, there is a lot of assumption you have taken, as you mentioned. So, there is a lot of uncertainty also. So how it will help the reliability when you apply the real model, means real-time model. And number three, that as the complexity is introducing one by one, so then together, how you can apply in the couple model or MOMS, what you are starting in the first slide. So how you can apply that? These are my few just questions.
So this is like, kind of like $1 million question, and that is the
definitely
we are all working towards that actually.
Yes.
And thing is that we have to be open-minded. That is like I feel like like acceptable, because I'm for my 4 years of my postdoc, I've never get accepted by community that this buoyancy forcing is important. They don't even care about this scaling. They feel like the scaling is only for the DNS until unless last couple of years when ocean model is actually showing the scaling. Okay, because then the things will change. And if this scaling is operated, that means it is a fundamental force balance. Okay, that means we have to say, for simple way, when I mention about this advection diffusion balance, right? Because it's the fundamental balance, because the heat has to be diffused and that get advected in large scale flow. This is like a way heat is moves, right? So that's balance there. But now, if I'm putting that balance in the interior of ocean, and then I'm not what is called, because that is the way we're talking about different flow. So that is actually what the Munch one-dimensional model is. Right? They also talk about advection diffusion balance, and they say, okay, we need a lot of mixing to get this support, and we are actually unnecessarily finding that mixing in the interior of ocean, which is not important. Maybe we should have to rely on this scaling and add the mixing in a place, which is observation maybe in these areas.
Exactly. Then what is the application of the DNS to the means GCM. And do you have not facing any problem during publishing the paper?
Yeah. My gyre takes publication of 4 years.
Do you convince the reviewer?
It rejected from Nature, Science Advance, finally GRL. But now people are
Accepted. Okay. Thank you.
It takes a lot of time, and it's very difficult for PhD student giving this problem.
Yeah, that's why I'm asking.
Now observation people saying ocean circulation is changing. So this is the I feel like if it's changing, is what thing is changing?
Yeah, it's very nice that the physical process is getting out from the DNS. But when they come to the application part, the reliability and generalized the way of reflection is very tough, very challenging to the community, particularly who are looking into the DNS and DNS to large scale. So large scale and small.
Then for a moment, like only few people, maybe they just think about when to is working with the convection.
Yeah.
But we need more people to work in this area so that we can actually translate. We do more work, so that translate it.
You are not doing it that to make it more generalized to fighting that reviewers and.
It is always difficult when you go against the convention.
Yeah. So thank you, Anupam. Any other question? Rahul has a question.
Sir, it was a very interesting talk. So I have this doubt that what is the time scale which you found in order it establish the overturning circulation with respect to you are comparing in the LES and model?
No, you never. Don't try to compare against the DNS and real system. The way we compared against some buoyancy time scale. Okay, and we also calculate the buoyancy time scale for real system because always there is a big mismatch. You see that time and space. So when you talk about second, it is not the second is in the real ocean. Okay, so we have to convert this time in terms of either a different number in the time. Okay, same is the forcing. We very difficult to convince. Like this is like very difficult for me in the establish this thing the ocean community because when I say 1 meter, how can you talk about ocean for 1 meter? Okay, so it takes a lot of time. Then I have to adapt. What is the language the community wants? I can't just continuously saying meter and publishing in a oceanographic journal, right? Because I have to translate this one. So that is the reason, I can take it in terms of this quantity and the quantity. And that is getting very clear to the community. Okay, this is I'm plugging the number for DNS and plugging for the number for the ocean. Okay, I got it this number. But you cannot compare immediate the quantities. Okay, we have to have a common ground, like that is a non-dimensional number. Okay. So it's like a kind of engineering approach to oceanographic, physical oceanography.
Yeah. Any other question? So if no one, I'll ask a question. Actually, what I understood from whole this exercise is that the density-driven currents are capable of generating gyres, for example, you are saying. But in your DNS simulation, that principle give rise to a lot of mesoscale meanderings around. So such mesoscale to generate, the condition for energy growth should balance that shear of the current multiply with the structure of the perturbation should we have a positive growth. How such a meager density current creates such a shear in the circulation to give rise to meandering as if in the Gulf Stream? In your DNS it shows. So isn't it an over exaggeration of the density-driven currents? That's my first skepticism, because wind-driven, once you have wind, the Ekman flow towards the south will set up the gyre because it has to be balanced by vorticity. Without that, density-driven currents be relying alone to generate such a shear in the flow in the ocean to have a meandering. So intense meandering. How you achieved it?
So as I told you, like of course, this is not comes in a one day because we are also playing around this. If sometimes we don't get it, we just constantly looking at what is actually missing. Is something is non-dimensional aspect is missing or not? Okay, so there's I just talk about a Rossby number. There's also called number as a number. Also the talk about Rossby deformation radius normalized by the depth of the thermocline. Like this is also playing a very important role because one time we have seen, as I told you, that we are not able to get this shear to have a meandering. Yeah, and then we thought about what is going on. Why we are not getting? We're getting everything is safe, but we are getting. Then we realizing the boundary layer thickness compared to the depth of the ocean in the DNS is not the same as the boundary layer depth against the against the depth of ocean in the reef system. Okay, so this is something we feel like, wow, this is another number is important, because think about in a deepness, if you increase the it's not going to happen. They are probably getting thinner, thicker and thicker. Correct. At the end of the day, they are going to extend the whole ocean depth. That is not the reef system. Is in the ocean, the thick is always 10 to 15% of the ocean. So make sure you are also this parameter region such that your boundary line and depth of ocean is right. Then you don't have to care about aspect ratio, because aspect ratio is not important. Important is the dynamics you are capturing in the top of the layer compared to the so then you're able to get the right share. Okay, then you get this right geostrophic share and then directly instability, and then you should re-entering. And certain things are changing. So and you see that I don't think this is the ocean, because we done several data points and this is looks like ocean, and then we are slowly understanding why is so ocean. Okay, and then we spend time to talk as this is the control case. This is the look like. I'm not saying it. This is the ocean. This is look like ocean, and then let's play around this ocean further down. Okay, can you understand it?
Yeah, thank you. So students who run ocean model can run an experiment. Switch off your winds, force the heat flux, see what happens from the non-moving ocean to moving ocean. It's a steady state problem maybe. I think that's what they are asking others to do also. We saw a paper in 2023 showed.
2023.
ROMs them they have.
This paper is rejected in JPO. Any paper, and so we people in the paper. It's rejected from JPO. Rejected from JPO because it is actually hitting that oceanographic community. They don't like it because the scaling is not. Usually we do. Why are you going to change the rotation? But until you change the rotation, how can you trace the scaling in all angle?
Okay, any other question? So otherwise we'll give a big thanks to Professor Gayen. Thank you for this. We invite you for a tea arranged there.
How that
You join in.
unless it comes into the GCM, no, the application or the gap, the gas is not going to be filled.
Yeah, I can see that.
So either drive the GCM community or you like, otherwise, this message will not. You are doing it for your satisfaction. How the ultimately you have to use a GCM, right? We cannot use it reality. How will it change that? How knowledge from here translated to that? That GCM community will never think about it. But you have to, because the DNS work has to progress, that has to be thought. Somehow, that in that case, the ocean community will accept approve this concept. Because of that, they're not seeing any sort of ways. Why depend and I'm getting very convinced by the team community. That's not this layer.